This paper is just 99% how they scaled the model, how they iterated on the data, and how they had these pre-training and what they're now calling post-training steps to take the model to the level of performance that we're seeing. All right, welcome everybody to Archive Dives with Oxen AI, where today we will be diving into the Llama 3 herd of models paper. And this paper is a behemoth of a paper at 92 pages. So we're going to be really focusing on the pre-training data preparation and then the post-training flow that makes this whole thing run. And you can find the paper on Meta's website. I'll be sharing this Notion page as we go along. So Llama 3.1 is a set of open weights foundation models that was released by Meta last month, July 23rd, 2024, if you're watching this in the future. And it's probably the most interesting paper that's come out recently. It has a lot of tactical details of the processes that went into building these suite of models. And it's important because this is the first time that one of these open models has caught up to the likes of GPT-4 or the Claude series of models from Anthropic or some of the other closed ones in the ecosystem. And what's cool is they released a whole herd of models. So an 8 billion parameter one, a 70 billion parameter one, and a 405 billion parameter one. And the 405 billion parameter one is really the one that's competitive with all of these other state-of-the-art foundation models. But they have some cool tricks of how they use the larger model to train the smaller models and improve the performance. So excited to dive into those as well. There's so many nuggets within this paper and so many like subtasks and subspecialties. I almost feel like this paper is like a guide to getting a job at a foundation model company. The list of credits at the end of the paper or list of authors is almost like a Hollywood movie of like how many people worked on this. So lots of interesting nuggets that we can take away. And what I think is one of the more interesting parts is that they keep the model rather constant between the Llama 1, Llama 2, and then finally Llama 3. It's really just your plain old dense transformer that we've seen over and over again that takes in the tokens, embeds them, has self-attention, feed forward, self-attention, feed forward, and then the output. They did do one or two tricks to extend the context length to 128K. But other than that, this paper is just 99% how they scaled the model, how they iterated on the data, and how they had these pre-training and what they're now calling post-training steps to take the model to the level of performance that we're seeing. And we love this style of approach at Oxen AI of just iterating on the data to improve the model, because that's what we are all about. So, like I said, they released 6 new models within here. Back in April, they released the Llama 3 suite, and that was an 8 billion and a 70 billion. And then in July, they released the 3.1, which has an 8 billion base, 8 billion instruct, and then base and instruct for all of the other sizes. What's cool is you can download these and run them on your own infrastructure, especially the 8B and the 70B. Just some rough math on the 405B, and they mention this in the inference section of the paper, but the 405B at 16-point floating point precision cannot fit on a single machine with 8 NVIDIA H100s. So they need to split it onto 16 GPUs across 2 machines. So just like kind of the back of the napkin math there is an H100 has 80 gigabytes of RAM. And if you have 8 of them on a single node, that's going to be like 640 gigabytes, but 405 times 2 is 810. So you need at least 2 nodes to split that across. And you can actually spin up machines like this in clouds like Lambda Labs. I just pulled up their spec for their new cluster product. And you can see here, you can actually spin up 2 nodes with 16 by 16 H100s, but it'll cost you like $71 an hour. And you can even spin up larger than that. But this would be like the minimum setup you would need to run the largest model, which I think is just keep that in mind as we're talking about the models that match GPT-4 in performance. So they kind of use 3 levers to improve Llama 2. And the 3 levers that they pull are data, scale, and then just minimizing complexity, which is part of the reason they stuck with the same architecture that they would had in Llama 2 and Llama 1 is they're like, since we're scaling this on so much data and so much compute, we want to make sure there's as minimal bugs as possible, keep it simple, stupid kind of thing. And I would argue that the data and minimizing complexity levers are 2 levers that any of us can kind of pull in these post-training steps. So I think there's a lot of nuggets that we can kind of pull from there. So the first one is data. And they worked hard on both improving the quantity of data and quality of data used both in the pre-training and the post-training. When it comes to the pre-training, they used 15 trillion multilingual tokens that they were careful to filter, mix, and balance before they even kicked off any of the pre-training. So if you think about that 15 trillion tokens, if a token is on average like 4 or 5 characters, it's probably like 8 to 10 bytes. That's like 120 terabytes of pre-training data. So that's a massive, massive data set. And so in order to process that data set, they needed to scale up their compute architecture. So you have like 120 terabytes of data that this model needs to crank through. And they said that they used 10 to the 25 flops of compute for this, which is hard to imagine. But this is 50x more compute than the previous Llama 2. And just like back of the napkin math for this pre-training step it's almost $1 billion of compute. Llama 2 was like $20 million, and this is 50x more than that. So not something that you can really do at home, but super grateful that they release these models so that we can fine-tune them on our own. And then the third one is just managing complexity. So they try to minimize the complexity in order to scale the model. And so this means they use a standard transformer. They use your basic supervised fine-tuning. They have a rejection sampling step that we'll talk about. They use DPO for the preference optimization, so no fancy RLHF or anything there. And so no real fancy bells and whistles that can be harder to optimize, just kind of vanilla transformer, supervised fine-tuning, all this kind of stuff, which I think is pretty refreshing that you don't have to be. We've seen all these tools in previous archive dives, so it's pretty easy to chain them together and see how this all works. So the 2 big parts of the paper that I want to dive into here are the pre-training steps and the post-training steps. And post-training, this is, I think, one of the first papers I've seen use that term. And it's mainly because before it was kind of like pre-training and then supervised fine-tuning and then maybe like an alignment step. But in here, they have an entire graph of post-training operations that they do. And they do the supervised fine-tuning and they do the DPO and they do it reward modeling. And they have a bunch of steps in the post-training. So they decided just to call it a big bucket of post-training instead of just fine-tuning afterwards. And so the pre-training step is your basic, just step by step. You have a massive corpus of text, and you're simply training this transformer to predict the next word. They did increase the multilingual data in this pre-training step to include German, French, Italian, Portuguese, Hindi, Spanish, and Thai, which is interesting because a lot of these are romantic languages that have a lot of similar tokens and can probably pick up from some things from each other. I thought Hindi and Thai were interesting to mix in there. I'm guessing it's probably just because Meta has a bunch of users in those languages, but those kind of struck me as outliers to the rest of the languages they picked for this model.
Hey, Greg.
And so, yeah, like
before you get too much further down, I just wanted I had raised my hand specifically for the multilingual thing. So just for everyone to wrap their heads around, it was 15 trillion tokens just for 8 languages.
Yep.
That's crazy.
And they even said that, most of these tokens are still English. And I think it's like, yeah, here's the final mix here. 50% of the tokens are general knowledge in English, 25 are mathematical, 17 are code, and then only 8 are these other languages. So it's still just predominantly English, and there's a lot more tokens we could probably get from these other languages. In order to collect all of this data, they use a lot of techniques that if you're ever wondering if you would ever use your like 101 machine learning text classification skills, this section of the paper is like text classification over and over and over again with a lot of filtering, cleaning, deduplication, and balancing of data sets. So the first thing that they do is, they take a giant web crawl like Common Crawl or, something like Find Web or something like that. That's a bunch of raw HTML documents. And they start by implementing filters designed to remove text that contains PII or adult websites or otherwise unsafe content. And these, they say, are just like a bunch of fast text classifiers. There's even this fast text classification library that comes out of Meta. And it was first trained to classify if a piece of text would likely be referenced by Wikipedia or not. So they kind of just have like a Wikipedia referenced or not classifier to filter out a bunch of junk. But they also have a more compute intensive transformer Roberta-based model to further filter and generate quality scores for every single document that they're planning on going through this pre-training step. So even this step on its own is super compute intensive. And like, we haven't even gotten to training the model yet. We're just trying to filter out tokens to get down to that 15 trillion. So clearly there was a lot more that they started with than 15 trillion. Next, once they figured out which documents that they want to keep, they wrote their own custom HTML parsers, and they optimized for both precision of removing boilerplate stuff like maybe ads or headers or whatever JavaScript that they didn't want, but optimized for precision of keeping the content itself. So they kind of have, custom classifier for all of this. And then they deduplicate all of the data at the URL level, the document level, and the line level. So what that looks like is several rounds of deduplication. The URL's pretty obvious. Document level deduplication, they use this min hash algorithm. Eric, I know you looked into that a little more. Do you want to give like a little TLDR on what a min hash filter looks like? Dedupe.
Sure. I mean, it's just an estimation of a more compute intensive like metric. There's a metric that basically looks at the ratio of the like they split the document into engrams. They look at the ratio of the shared engrams to the unique engrams, or really the total engrams, but that includes the unique ones. And then they have a min hash algorithm to estimate that, and it's a measure of similarity.
Yep. So they're trying to get as many unique documents in here as possible. And then they do this line level deduplication, which is also an interesting method where they remove lines that appear. Well, first they bucket the documents into 30 million documents per bucket, and then they remove lines that appeared more than 6 times in each bucket. And they did some like manual qualitative analysis that showed that this works well. But lots of pre-processing here, and I imagine there's an entire pre-processing team that does all of this stuff before they even get to model training. They also did some heuristics around filtering low quality documents, such as ones that repeated themselves a lot, contain dirty words, or super uncommon words is one of the things that they mentioned. And I thought that was interesting because I remember in my early days of training language models, we would always talk about Zipf's law, if you guys are familiar with this. And it's kind of how the distribution of counts of words in a corpus goes down logarithmically pretty fast. And we would actually do the reverse, where we would try to filter out documents that only had common words here, and tried to surface up documents that had more uncommon words so that the model could learn more about them. So I think what they're saying with this filtering out documents that repeated themselves or have super uncommon words, I bet it's documents that only have super uncommon words, because those are probably more likely garbage than interesting content. But I thought that was an interesting choice of words that they used when they were filtering out this stuff.
May
Yeah,
I add on to
solid
that
gold
actually?
Magikarp.
What's that?
Sorry. Go
Yes,
ahead.
solid gold Magikarp. That's funny.
Yeah.
I'd like to add on to that by saying they tested like the whole document itself. If the document itself was an outlier, like compared like with its KL divergence, if the whole document was an outlier compared to the other documents, they removed it.
That's a good point. Yeah. So it's probably just more of a garbage document than like any tokens we actually want to learn. Cool. Um,
I'd
and
love I'd
then,
love to see their list of uncommon words.
right? Yeah, it's
Did
actually
they
pretty, they
did
don't
did they
have,
include that?
no, they don't. But it's a fun, just like 101 NLP exercise to just count n-grams in a corpus and then sort by rank and then like go to the 500,000 n-gram or something, and you'll be like, whoa, I either didn't expect that word to be so far down, or I've never even heard of that word
Yeah.
before. Yeah.
So I wonder how that affects things like medicine and chemistry
Yeah.
performance.
Yeah. So I think one of the big things that they were trying to optimize for this model is a general purpose model. And they weren't focused as much on those specific tasks. So I think
Right.
that was partially an intentional choice. But they did have specialized pipelines for code and reasoning data, because those are tasks that they did want it to do really well on. So they also have these classifiers as they're going through all of these documents to be like, is this document code? Does this document have LaTeX or math in it? And they actually have a different cleaning pipeline for those specialized types of data. Doesn't go through the generic HTML parser, because they want to preserve the code or the math or the LaTeX like in its own content. So I thought that was pretty interesting. And for the multilingual data, they actually classified the data into 176 different languages, but only kept those 8 or 9 or so, which I thought was interesting. And I'd be curious to see what the distributions of those other languages were, but they didn't really talk about that much. So that's kind of like collecting the pre-training data. But when it comes to the full pre-training recipe, they do what they call the initial pre-training, which is kind of that data mix that I showed you before of 50%, 25%, 17, and 8. They train on all of that together. And then, so that's like the 15 trillion tokens. Then they do all of that on a context window of, I think it was 4 or 8K. Do you remember, Eric, how big that initial context window was?
It was an 8K original context length.
Yeah, and then do you want to talk about how they kind of scaled up to the long context?
Sorry, can you say that again?
You want to talk about just how they kind of scaled that up incrementally at the end with smaller data sets?
Yeah. So what they did is at the final stages of training, they did an extra step where they incrementally increased the context length over about 6 different like steps. They would increase the context length and include like longer context data. And then they just train it at that context length until it got to the standards they set, which were, first, it has to recover its original performance on like the short context evaluations. So it has to be at least as good on the short context stuff. And it also has to solve the needle in a haystack with like 100% accuracy.
And then they can bump it up to the larger length and larger length. And
Right.
what, it was probably like a doubling each time till they got 128 or something like that.
Most likely a doubling, yeah. But that also shows that just increasing the context, which we kind of already knew, but just increasing the context originally degrades performance at all context lengths. So theoretically, it maybe would have been even better on the short context stuff if they had never done the context length increasing. So that's interesting.
Yeah, that's an interesting point.
But then they got it up to 128K by the end of the 6 training steps, which took 800 billion tokens to do.
Yeah, so 800 billion of that 15 trillion was just for long context. And then, yeah.
Just going back to the data filtering, one thing I found interesting was that they said that they found Markdown to be harmful. And I don't know, that seems kind of counterintuitive to me. It seems like training it to write in to respond in Markdown would actually be helpful for structuring those outputs.
Yeah, I also found that interesting, and I couldn't think of a reason why that would make sense to filter that out. But I think, did they say they filtered out? Oh, you have an idea?
Speculations.
Yeah.
Well, I think Anthropic figured the same thing out because they say prompt Claude with XML, not Markdown. And I also saw people do experiments with various models, and Markdown did basically like no better than raw prompting, but XML actually did better, which was interesting. And I think the reasons for that are mainly, I mean, Markdown isn't everywhere on the web because it's they parse
it's
the
rendered into
HTML,
HTML.
right?
Yeah.
So the majority of the training data is going to be raw text. And adding Markdown kind of forces it to like switch gears potentially. So maybe it's not obvious right away, but apparently it like empirically it just turns out that forcing it to do that as well maybe makes it worse. So I mean, it's interesting, but I do think XML is a better format for language models in general, just to like format your prompt in, because it gives it like tag or like an opening of the tag and a closing of the tag, which kind of wraps the text, which may be good for it. like locating that text when it needs to retrieve information from that text.
Yeah, those are all good points.
That kind of ties back to my my rant about people using HTML strike through tags for beginning and end of sequence tokens, the special tokens,
Oh, interesting. Yeah,
the S and /S.
right. I didn't even think about that. It's a good point. Cool.
That is
So yeah, that was long context. That was some of the pre-training. And then they have this final step that's kind of interesting where they have these domains that they want it to do really well on. So they left out, or they like code and reasoning and math, and they would continue the pre-training at the end and make like a specialized pre-trained code model. And you'll see this kind of later, how they use that specialized code model, but they said that that's like a form of simulated annealing where you kind of like optimize for different paths with different data sets. And then they combined those models at the end to have like the final base model. But they actually didn't have too much detail on the annealing. It was just a few sentences there.
They also annealed the learning rate itself down to 0.
Yeah, it's a good point. So they progressively linearly changed the learning rate to 0 during that annealing process.
And they took 40 million tokens to do this.
40 million. Yeah, so 40 million super high quality tokens at the end for this part.
If anything, I wish they released that data set.
Right? Yeah, because they did. So with all of those classifiers and all of those Roberta ranking models and whatever, they ranked all of the data and said this 40 million is awesome. So that would have been good to maybe release a subset of it, but that's their secret sauce, I guess.
I'd like to point out, by the way, if that's fine, the reason that they had to do that is because they found, especially for the smaller models, but not so much for the larger models, training it one way, like with the data mixed all around, led to poor performance on those specific tasks and fine performance like on more like general reasoning tasks and stuff, or like general like English tasks. But putting those tokens at the end didn't really hurt the performance on the general like English tasks, but it did improve the performance for the math and code, which shows that those are probably harder tasks for the model to learn, which I mean we figured, but there's something different about them. And also, it's interesting that the larger model didn't really run into the same thing. They said the larger model got very little benefit from the annealing compared to the smaller models.
That's an interesting point. Yeah, I wonder if part of that's even just like some catastrophic forgetting, like the model doesn't have enough parameters to encode, so it kind of like keeps the latest things better. I don't know.
That is something I did speculate.
Yeah.
Hey, Greg, in the chat, Kaiser Pister made a comment that from earlier that I thought was interesting. He says, if we lump all the initial learning into quote pre-training and all the alignment stuff into quote post-training, what is just the training step? And actually, one of the researchers, I don't remember who, like you'd recognize the name. I don't remember if it was Jan or Jeremy Howard or someone like that. One of the people you follow that I follow because you follow them. They went on a rant about this exact point. And when they were on a rant about simplification, like let's just call it, they're all large, so let's just call it language models, not large language models. And
interesting.
And then this point he put here in chat was this another point, almost exactly. So it's kind of funny, but
yeah, because even when we dive into these steps here and here, like these are just language modeling steps, and you have a language model that comes out of it. So yeah, it is interesting that they are categorizing the training into different steps, but at the end of the day, it's all training. Cool. So now we're going to dive into the post training, and this I think is where it gets interesting, probably for the rest of us who aren't going to do this 15 trillion token pre-training unless you work for one of the big companies. And they have this diagram here of the post-training is actually super similar to the self-rewarding language model paper that we did at the start of the year. So Raul, I think, who was on the call here, actually implemented a lot of the code for a self-rewarding language model loop. And that paper was from the team at Meta as well. So no surprise that they used some of those techniques, and we'll see how they actually improved that kind of loop with a separate reward model, a separate SFT model, and then a DPO step. But we'll kind of walk through this whole diagram and each step of how it worked. And they do this whole loop 6 times, generating synthetic data pretty much all the way through, and then like filtering out synthetic data and keeping the best data as they go along. So there's 2 main models that they want you to pay attention to, and it's a reward model and a language model. So this is a language model, this is a language model, and then this is a reward model. And the first thing that they do is they collect a bunch of human annotated data. So this is like the collect prompts step up here. And they didn't give like a raw number for how many prompts they started with, which I think would have been super helpful to know. But the first step within this whole process before they kick it off is they have a list of prompts and they generate K responses for each prompt. So that's, I think they said the number for K here was anywhere from 10 to 30 responses for each prompt. And then they had humans go in and annotate all of these responses. And this is to train the original or the first reward model. So basically what they do is they have 3 categories of responses for each prompt. So in the simplest case, if you had 1 prompt and generated 2 responses, one of the responses is going to be better than the other one. So you would put the better prompt in the category of chosen and the worst prompt in the category of rejected. But they added a 3rd step in here since they had humans labeling all of this data. And they said, okay, but the one that you choose, edit it to make it even better. So they added a 3rd category of edited is better than chosen is better than rejected. So that's kind of like the first step here is a lot of manual human labor. And now that they have a bunch of data of a prompt, a response, and what category it belongs to, they train their initial reward model that can take a prompt, a set of responses, and kind of give you a score for how good this response is given this prompt. So that's what they call the reward model, and that's kind of on the left-hand side here as they're going through this loop. And what's different from the self-rewarding language model paper that we talked about earlier in the year is the self-rewarding model, they tried to have the same model be the reward model and the language model itself. And so just like splitting those into 2 models lets the reward model just specialize on, is this good data or is this bad data that's coming out of the loop?
I'd like to add in because there's a couple details to add. First of all, they used multiple versions of the model to generate the prompt responses. Like, for example, they have a model that had slightly more coded data or a slightly older version of the model or various like different things to get more diversity in the outputs. Also, the human evaluators rated the prompt as well, or sorry, the response as well about how much they preferred it.
Yeah, so these categories
I prefer this. It's significantly better versus it's not that much better.
Yeah, I thought these were interesting distinctions. Slightly better or marginally better. So they actually had like 4 categories, and then in this step, when they're doing the filtering down and to put the synthetic data back in, they're like, it has to be significantly better or better to keep it. Is that right, Eric?
Yeah. They took the top two categories. Also, it did do a little bit of self-rewarding because they did use, I believe they, if I'm not mistaken, they did use Llama 3 to judge the data. I don't know if it was in this step precisely, but I think it was.
Yeah.
They used two different evaluators, right? In a lot of cases, they used Llama 3 itself, like the current version of it, with a detailed prompt, and they also used a plain old like reward model, and then they like averaged the scores basically a lot of the time, or like took both into account.
Yep. So they would have like a reward model score that's just like a floating point number, and then they would have like a prompted llama that says, is this better than the other? And then they would like output some text, and they would use both of those to decide whether the synthetic data should come back in to the loop. Cool. So that is the reward modeling half. And again, if you think of like components within here that teams might work on, this is probably a whole team that's just working on training the reward model itself. And like, you have to be really good at machine learning and classification and to get that reward model really well to make sure that this whole loop doesn't degenerate. So then the next part is the SFT data, or the supervised fine-tuned data and model. So this data consists of data from the human annotated collection with the rejection sampled responses, as well as synthetic data targeting specific capabilities. So later down in the paper, they have like 7 or 8 different categories where they generate specific synthetic data for it. So like code, for example, or tool use. They have different SFT pipelines for generating those specific types of synthetic data, because they kind of have different properties as your generic data, and we'll dive into that a little later. And so the quality of the synthetic data is really important here, since a lot of most of the training data is actually model generated and not human generated. It requires a lot of careful cleaning and quality control as it goes through this pipeline. And some of those are just pure like deterministic rule-based filters to reject obviously bad text from earlier iterations of the models. Like they might have a regex that's just don't have this many exclamation points or emojis or something like that. I also thought this portion was pretty interesting, where so this is where they're saying most of our training data is model generated, quality control, and in the early rounds, some of the responses might be overly apologetic or have tonal issues. Identify phrases such as "I'm sorry" or "I apologize" to carefully balance the proportions within the data set. So they even tried to balance like the tone that's coming out of the model. And I'm pretty sure they had both model-based approaches to this and just like regexes to make sure that the model that's going back in is pretty diverse.
They probably also tried to detect if it was repeating itself or got caught in a loop like that, because that can happen.
Yep, totally. And what I thought was pretty funny is, Cameron, you remember your like unanswerable questions or impossible questions? I remember I ran them all through GPT-4o, and it was pretty funny how often it repeated itself at the start, because these are all questions that are like kind of trickery or don't have an answer. And the amount of times it was like, oh, comma, oh, sure, oh, well, and like it has the same responses every single time. Wow, well, oh, sure, So I thought that was a pretty funny example.
The classic it's come up with a classic evasive machine language comment to say something when it doesn't really know it, but it doesn't want to admit it doesn't know it.
Exactly. Yeah. So this is the type of stuff that they were trying to mitigate against in that step. Let's see what else. So we talked about, yeah, they used models to filter out the score. They also looked at how difficult so they had like a quality score of how high quality the prompt and responses are, but also a difficulty score. And so, like Eric said, they had some both Llama-based and Roberta-based models to cluster responses, try to semantically deduplicate them, and also pick ones that are high quality and difficult. So like they're not just putting this in a loop and letting it go. They have a lot of checks within the synthetic data itself to make sure it's high quality data going back into the system.
They also did rejection sampling to make the model generate like 30 different responses, and they took the best one from those.
Yep, exactly. So if we kind of go through this whole pipeline again, talking about everything I just said, collect the prompts, generate 30 responses, like Eric said, use the reward model to decide which one of those responses are high quality enough to go into this supervised fine-tuning data. They supervise fine-tune a model. And then this is where it gets interesting as well, is you'll see these specialized per capability SFT data, and then pairwise annotated specialized per capability binary preference data. So the next section, I think, is honestly one of the most interesting and tactical sections, and it's all about the capabilities of the model. And if you want to kind of skip there in the paper, it's section 4.3. And so they kind of stack ranked what the capabilities they thought would be most useful for end users and like what people are most likely using these models for. And so they have 7 categories here of they want it to be really good at code. They want it to be multilingual or be able to translate between languages. They want it to be good at math and reasoning. They want it to be good at long context, good at tool use. They want it to be factually correct and steerable by the user. So each one of these kind of has its own synthetic data generation pipeline and its own per capability SFT data that's going in, and its own per capability binary preference data that goes into the reward model. So I almost feel like each one of these could be its own like archive dive or practical dive in itself. If that's interesting to you guys, we could go into all of them in separate like shorter YouTube videos or something like that. But with the time that we have left, I want to go over code just so you can get a sense of all the custom things that they did for code in a synthetic data generation sense. So for code, they prioritized Python, Java, JavaScript, C, C++, TypeScript, Rust, PHP, HTML, CSS, SQL, Bash, and Shell. And what they first do is, so remember in that pre-training step when we talked about they segmented out a lot of code data and continued the pre-training just on code at the end? Well, they took like in that pre-training step, they made sure that it was 85% code and 15% the other stuff. And they trained a code expert model that they used to collect high quality code examples that were then passed to the human to annotate. So they said that during this step, they generated 2.7 million synthetic examples just for this SFT for code. And they kind of focused on 4 different areas of this code generation and code skills. So they said that often these code models have difficulty following instructions, difficulty with syntax errors, difficulty making sure the code generation is just correct, and then how do we get it to fix bugs? And what I thought was interesting here is they have this quote where they say, while intensive human annotation could theoretically solve these issues, synthetic data generation offers a complementary approach at a lower cost and a higher scale, and is unconstrained by the expertise level of annotators. So super interesting that they are arguing that at this point, the model is actually better and cheaper at checking its own work than humans. And you'll see kind of like the tips and tricks they do to make this the case. It's not just like the model is better at this out of the gate. But they say, especially with the 8 billion and the 70 billion parameter models, when they use the 405 billion parameter model to generate the data, it just upskills those smaller models much quicker. So how do they do it? First, they generate a problem description. So what they do is they sample a random snippet of code from various sources, and then they prompt the largest model to generate programming problems inspired by the code snippet itself. So they start with a little snippet of code, and then they have a prompt to say, like, what would somebody ask to generate this snippet of code? So then they kind of separate out the problem description from the code snippets, and they say, okay, now that we have all of these problem descriptions, now generate me a solution. So they prompt the model to then solve all of these problem definitions in multiple different programming languages. So you can kind of see how they start from real code snippets and kind of explode the number of examples to problem definitions and then solving those in different programming languages. They also add like general rules of good programming to the prompt during this solution generation. So I don't know, they might take like the pragmatic programmer book and have some tips at the top of the prompt that say like, be concise and don't repeat yourself or whatever. So I thought that was an interesting way to start from real data, generate synthetic questions, generate synthetic answers, and do it in a bunch of different languages. But of course, when you do this, you're going to generate a bunch of solutions that aren't actually correct. So after generating a solution, they need to check if it's correct. So they do a few things. They first pass it through a bunch of parsers and linters for that programming language to try to catch syntax errors and other things that you can check with static analysis. But they also have the model generate unit tests to see if you can compile, run it, and they pass the unit test itself. So a lot of synthetic data, and then they filter it down by linters, parsers, unit tests, etc. And then if it fails, any of the linters fails any of the unit tests, they have this error feedback / self-correction mechanism. And so they kind of include all of the errors from the parsers, linters, or unit tests, put that back into the prompt and say, can you fix this? And they said about 20% of the initial solutions, the solutions that were initially incorrect, were able to be self-corrected by just putting the errors back into the prompt and running it again.
I proposed that for code model training several months ago. So cool to see that.
Cool to see it in action. Yeah. And then they do the standard like 6 iteration fine-tuning iteration approach that we saw above. And they kind of described these out of order, but this last one I thought was super interesting too. When they had lower resource languages like TypeScript or PHP, they actually used a specific model to translate from the higher resource languages to the lower resource languages. And basically what they would do is, so they would have, a snippet of Python code, and they would say, generate a snippet of PHP code. And they first generate the snippet of PHP code, and then they backtrace it, back translate it, and say, okay, now that we have PHP, go back to Python. And so now you have two Python functions, and they have a model say, are these two Python functions the same or not? And they assume that if it can go both ways, that the translation is correct. So I thought that was also an interesting technique to kind of get more data in more languages. So that's kind of where I stopped for the day, because it's a 92-page paper. And like I said, there's a section like this code section for each one of these capabilities or skills that it's trying to add. And I honestly think each one is super interesting on their own. So happy to dive into those in subsequent dives, or maybe we can have some example Oxen data sets of each one of these. I think tool use, factuality, steerability, those would all be super interesting data sets. But let us know if you guys find that interesting. And so, yeah, in conclusion, a 92-page paper of just tons of practical implementation details. Each section and each step within the paper is like a full engineering team in itself. And I thought this was just pretty spectacular, was like the list of core contributors. There's actually 3 or 4 pages that look like this of all the people that worked on this project. It's like you're scrolling the credits of a Hollywood movie at the end. So a lot of resources that they put into this, and the fact that we can just grab the 8 billion, 70 billion, or maybe run the 405 billion through an API, I think really opens up the things that we can build and not have to, be tied to these closed source models. So that is all I had for today. I'll kill the recording. Thanks if you're watching on YouTube, and we'll just chat for the next 5 minutes if there's any kind of async questions. Thanks, guys.